Okay, let's do a harder question now on tree diagrams. This one is called a dependent event because one event affects the outcome of the other. They're not independent, they are relying upon one another. So here, there's a bag of marbles, 6 red, 4 white, and George removes a marble at random, but he doesn't put it back. So let's try and fill out the probability tree based on this information. So like I said, there are 6 red and 4 white. So the probability he picks a red, there are 6 reds out of a total of 10 marbles. The probability he picks a white, there are 4 white marbles out of a total of 10. So let's assume this first event happens. This is the first event, the second event. And the first event is him picking out a marble. So let's assume the red did come out. What's the probability of him picking another red? Well, if he's picked a red, we're now 1 less marble in the bag, and he's gone from 6 marbles to 5 marbles. And the fact that we know these two must add up to 1, we know straight away this is 4 knights. But even if we didn't do that way, we could say, okay, there were 4 white in the bag to start with. He's not picked a white. We've still got 4 whites left out the 9. Forget that happened. Now let's assume this scenario happened. He didn't pick a red, he picked a white. If he picked a white one out of the bag, what's the probability that he picked another white? Well, he's got 1 less marble in the bag. There's now only 9, and he's gone from 4 white ones to 3. But if he didn't pick a white, he picked a red. Well, we picked a white first, so there's still 6 red marbles left in the bag out of a total of 9 because the white one was already picked. So be really careful with your denominators here because they reduce. Anything to do with food, if it's sweets or cakes, cookies, they get eaten. They don't get replaced. No one picks a sweet and then puts it back, unless it's one you don't want. So you can assume anything to do with food, without replacement, it's gone. The cake has gone. Anyway, next part says, find the probability that the 2 marbles are the same colour. Well, we could have a red and then a red, so that one there. And then here, we could have a white and then a white. So we've got 2 scenarios here, red, red, and white, white. So let's work out the probability of a red and a red. We multiply across the tree. So we do 6 out of 10 times 5 out of 9. So 6 times 5 is 30. 10 times 9 is 90. Now let's do this bottom one. White times white. So white, white. We have 4 out of 10 times 3 out of 9, which gives us 12 out of 90. Now, personally, I wouldn't cancel at this stage. And the reason is you are now going to add these 2 together. And if you've cancelled, the denominators might now be different. So wait until the very end to do any cancelling. So we want the probability of the same colour, which is white, white, or red, red. And we know that or means plus in probability. Probability of white, white, plus the probability of red, red. Now let's add them together. White, white, sorry, I put it the other way around. White, white, 12 out of 90. Red, red, 30 out of 90. We add the denominators together. 12 plus 30 is 42. Remember, we don't add the denominators. We add the numerators, sorry, not the denominators. That stays the same. And then you can start cancelling down. I'd just divide by 2 to start with because they're both even numbers. And we get 21 out of 45. Hopefully something in your brain says, oh, they're both in the 3 times table. So you can do 3s into 21, 7. If you struggle to know this one, you can obviously set yourself up a little short division here if you want to. Or you can go straight into it. It's entirely up to you. 3s into 4 goes 1, remainder 1. 3s into 15 goes 5. And that's your answer. All finished.